In this first video, we are going to define a mathematical sequence, and then we're going to take a look at some examples. So let's get started. All that a mathematical sequence is just a list of numbers. Now, we choose to use the notation for a sequence to be a little bit interesting because there are two things that are important to us, which are called the term in the sequence and the index of the term. Kind of thinking of if you're a customer at a store and you have to wait in line before you can go up to the register. We keep track of who the people are in line and also their place in the line. The same is going to be true of a sequence. We want to keep track of the term in the sequence, what the number actually is, but we also want to keep track of its place in line. That's what the index is. And so when we talk about a sequence, A sub n is the term. That's the value of the number in the list. And then just that little subscript part is called the index of the term, and that's its place in line. So the example here is that we have a list of numbers, 3/10, 3/100, 3/1000, and we would continue on. And the first term is 3/10, the second term is 3/100, the third term is 3/1000. Those positions are the indices of these terms. Now, a mathematical sequence is just any old list of numbers. We could just start spouting off numbers at random, and that would be a mathematical sequence. But one of the biggest overarching themes when we're studying mathematics is the study of patterns and predictability, and that will absolutely be the case for us right here. So although a mathematical sequence could be any old list of numbers, we're going to be particularly interested in lists of numbers that form a pattern where we're going to have some ability to predict what might come next in that list. So if you take a look at the example I've chosen here, I've chosen to list off numbers in my sequence that have a predictable pattern to them. If I think of 3/10 as 3/10 raised to the first power, and 3/100 as 3/10 raised to the second power, and 3/1000 as 3/10 to the third power, we see that we could use the function 3/10 to the n to describe the nth term in the sequence. And that's really powerful. I only listed 3 terms of this sequence, but because I have a very special kind of sequence, one that exhibits a pattern, I could predict the 100th term in this sequence with no difficulty at all. That's going to bring us to our very first exercise. So what I'd like you to do if you're watching at home is pause the video and do for each one of these sequences. I've provided 6 sequences for you. Make sure you understand the sequence by listing out the next 3 terms. Then see if you can have that same predictive power we had on the previous slide. See if in your head you could envision what the 100th term in the sequence would look like. And last but not least, see if you can come up with a function or a formula like we did on the previous slide that predicts the nth term in general. So I could change that 100 to a 1,000, 1,000,000, 452, whatever I want, and still know exactly what that nth term would be. So go ahead, pause, and work out these 6 examples. And when you're done, unpause, and I'll reveal the answers on the next slide. All right, answer time. From the 6 sequences on the previous page, here are my nth term formulas. So I only did part 3 here because given part 3, I could answer parts 1 and 2 automatically. I don't have much to say about the first 3. Hopefully, none of them was particularly challenging, but if you have any questions, be sure to let me know. 4 is where things start to get a little bit interesting. For example, you look at -1, 1, -1, 1. You can see the pattern. You may have been very easily able to do parts 1 and 2, list the next 3 terms, and even predict the 100th term, saying, I see, whenever my index is an odd number, I'm at -1, and whenever my index is an even number, I'm at 1. However, you may not have been able to come up with this formula. That's perfectly all right. It's kind of a trick. We're going to look at -1 to the nth power. When n is odd, this will be -1. When n is even, this will be a +1. This formula is a very important one that comes up in mathematics a lot, so I really just wanted to take the opportunity to show it to you. This is sometimes called an alternator, because what it does is make the sequence alternate positive, negative, positive, negative. Once you have that cute little alternator trick up your sleeve, you can take a look at a sequence like 5, and you can break it down into little parts. I have 2 minus something, 2 plus something, 2 minus something, 2 plus something. All right, so my pattern should be 2 plus my alternator, so that it will go minus plus, minus plus, minus plus. That's what this part will change into. And then on the first term, I'm subtracting 1. On the second term, I'm adding a half. On the third term, a third. The fourth term, a fourth. That's easily represented with a 1 over n. And so breaking up a more complicated sequence into little parts is another really good practical technique. Now, last but not least, in sequence 6, this might have been a pattern that you struggled with. And again, because it's something that will come up a lot for us in calculus, I wanted to take the opportunity to talk about it. The formula I use to describe this pattern is 1 over n factorial. So that's what the exclamation means. It means factorial. That may be something you've seen before. If so, awesome. If not, if you were looking at that exclamation mark like, why is she excited about 1 over n? Or are we excited because we're at the end of the exercises? I don't know. The exclamation mark is an abbreviation that we use in mathematics that I'll describe more in the next video.